Welcome to DAR Tutors for online and home tuition. In this video, we will explore the topic of logarithms, a fundamental concept in mathematics with wide-ranging applications, particularly in the sciences and engineering. The content we cover is designed to align with the IB Mathematics, Applications and Interpretation higher-level curriculum. By the end of this session, you will be able to, first, understand the definition and basic properties of base 10 and natural logarithms. Second, apply the essential laws of logarithms to simplify and solve expressions. Third, sketch and analyze logarithmic functions, including their transformations. And fourth, use logarithms to solve real-world problems involving scales, decay, and growth. Our first objective is to define logarithms in base 10. You will learn what a logarithm is and how it relates to exponential form. We define the logarithm in base 10 of a positive number as the power to which 10 must be raised to obtain that number. This definition creates a direct link between exponential and logarithmic forms. If y equals 10 to the power of x, then we can write this relationship as x equals log base 10 of y. Here about log base 10 of y asks the question, 10 to what power equals y? We often omit the base 10 and simply write log y. So, log e is a shorthand for log base 10 of y. Let's look at a few examples. What is log base 10 of 100? We need to find the power that 10 is raised to get 100. Since 100 equals 10 squared, the logarithm is 2. So, log 100 equals 2. Next, consider log base 10 of 1/10. To express 0.1 as a power of 10, we know it's 10 to the power of negative 1. Therefore, log 0.1 is negative 1. Finally, let's find the logarithm of the square root of 10. First, we write the square root of 10 in exponential form, which is 10 to the power of 1/2. Since we are looking for the power, log of the square root of 10 is simply 1/2. These were examples where we could find the logarithm by inspection. However, for most numbers, we need a calculator. For instance, log 34 is approximately 1.53. This means 10 to the power of 1.53 is approximately 34. From our definition, we can deduce a very important identity. Since x is the logarithm of 10 to the power of x, it means that if you raise 10 to the power of the logarithm of 10 to the power of x, you just get x. This simplifies to the key identity. 10 raised to the power of log x is equal to x for any positive x. This shows that the exponential function 10 to the x and the logarithm function log x are inverses of each other. So we have now defined what a logarithm in base 10 is and established its fundamental relationship with exponential functions. Our next objective is to simplify logarithmic expressions by applying the 3 core laws of logarithms. You will learn these rules for multiplication, division, and powers. The first law deals with the logarithm of a product. It states that the logarithm of a product of two positive numbers m and n is equal to the sum of their individual logarithms. So, log of m times n is log m plus log n. The second law is the quotient law. It tells us that the logarithm of a quotient, m divided by n, is the difference of their logarithms. That is, log m minus log n. The third and final law is the power law. This rule is particularly useful. It states that the logarithm of a number m raised to the power of p is equal to p times the logarithm of m. We can take the power p out as a coefficient. These laws are powerful tools for manipulating logarithmic expressions. Let's see them in action with some examples. First, let's use the power law to simplify log base 10 of 1/8. We can rewrite 1/81 as 81 to the power of negative 1. Now, applying the power law, we bring the exponent negative 1 to the front. This gives us negative log 81. Let's try a second example. Combining the quotient law with the fact that log 10 equals 1. Show that log 500 can be written as 3 minus log 2. We can write 500 as the quotient 1000 divided by 2. This is useful because 1000 is a power of 10. Applying the quotient law, this becomes log of 1000 minus log of 2. We know that log 1000 is 3, because 10 to the power of 3 is 1000. So the expression simplifies to 3 minus log 2. We have successfully applied 2 different logarithm laws to prove this identity. We have now reviewed the 3 fundamental laws of logarithms for multiplication, division, and powers, and demonstrated their application in simplifying complex expressions. We will now introduce another important logarithm, the natural logarithm. By the end of this scene, you will understand the concept of base e and how to work with natural logarithm expressions. The logarithm in base e is called the natural logarithm. The number e is a special irrational number, like pi, approximately equal to 2.718. The natural logarithm of a positive number x is commonly represented as L side ix. It asks the question, e to what power equals x? So if y equals e to the power of x, then ln of y equals x. This means e to the x and ln x are inverse functions. This inverse relationship leads to two key identities. The natural logarithm of e to the x is x, and e raised to the power of the natural logarithm of x is also x. These are the same cancellation properties we saw for base 10 logarithms, just with e instead of 10. Let's work through some examples involving natural logarithms. First, simplify ln of e cubed. Because ln and e are inverse operations, they cancel each other out, leaving us with just the power. 3. Next, let's simplify e to the power of 2 times the natural logarithm of 5. First, we use the power law for logarithms to move the coefficient 2 into the exponent of 5. This gives us e to the power of ln of 5 squared. Now, we can use our cancellation property. E to the power of ln of x is x. So our expression simplifies to 5 squared, which is 25. This shows how combining the laws of logarithms with the cancellation property can greatly simplify expressions. To solve for a variable inside a natural logarithm, we use the inverse operation, exponentiation with base e. Let's find x if ln of x equals 2.1c. To isolate x, we unlog both sides by raising e to the power of each side. This gives x equals e to the power of 2.1c, which, when calculated to 3 significant figures, is approximately 8.76. Therefore, the solution to ln x equals 2.1c is x is approximately 876. We have now defined the natural logarithm in base e and demonstrated how to use its properties and its inverse relationship with the exponential function e to the x to solve problems. We will now shift our focus to logarithmic functions. The objective here is to understand the relationship between exponential and logarithmic functions and to sketch their graphs. We've already established the fundamental identity. 10 raised to the log of x is x. This identity shows that the logarithmic function, y equals log x, is the inverse of the exponential function, y equals 10 to the x. The same relationship holds for natural logarithms, with I equals ln x being the inverse of y equals e to the x. Graphically, the inverse of a function is a reflection across the line y dy equals x. This means we can sketch the graph of a logarithmic function by reflecting its corresponding exponential function. Let's start with the exponential function y equals 10 to the x. It passes through the points 0, 1, and 1, 10, and has a horizontal asymptote at y equals 0. Now, to find the graph of its inverse, y equals log x, we swap the x and y coordinates of the exponential function. This means the points 1 and 1, 10 become 1, 0, and 10, 1 on the log graph. The horizontal asymptote at y equals 0 becomes a vertical asymptote at x equals 0. The graph of y equals log x therefore passes through 1, 0, and 10, 1. This point, 1 us, is the x-intercept. Let's compare the key features of these inverse functions in a table. For y equals 10 to the x, the domain is all real numbers, x is an element of R, and the range is y is greater than 0, meaning it's always positive. It has a horizontal asymptote at y equals 0. For its inverse, y equals log x, the domain and range are swapped. The domain is now x is greater than 0, and the range is all real numbers. It has a vertical asymptote at x equals 0. We can transform these basic functions using the same rules we've applied to other functions. Consider the function f of x equals 2 ln of x minus 1. Let's describe the transformations from y equals ln x. The coefficient 2 represents a vertical stretch with a scale factor of 2. The minus 1 represents a vertical translation 1 unit downwards. The domain remains x is greater than 0. The range remains all real numbers. To find the x-intercept, We set f of x equal to 0 and solve for x. This gives ln of x equals 1/2. Using our inverse operation, x equals e to the power of 1/2, which is approximately 1.65. This confirms that the graph crosses the x-axis at about 1.65. We have now defined logarithmic functions as inverses of exponential functions, sketched their graphs by reflection, and seen how transformations affect their key features. We will now explore one of the most powerful applications of logarithms, scaling. You will learn why we use logarithmic scales and how to interpret them in real-world contexts. In many real-world situations, quantities vary over an enormous range. For instance, the energy released by an earthquake or the intensity of a star. Using a standard linear scale to represent these values makes them impossible to compare. Small values are clustered near 0, while large values are compressed into a single distant point. To address this, we use a logarithmic scale. The process involves taking the logarithm of each value. Because logarithms turn multiplication into addition, a logarithmic scale transforms large multiplicative changes into much smaller, more manageable additive changes. To form a simple logarithmic scale, we take the base 10 logarithm of each value. The major tick marks on this new scale are equally spaced, and each corresponds to a power of 10. We often say that each step on a logarithmic scale represents an order of magnitude difference. Let's look at an example. Consider this logarithmic scale, scaled using the function y equals log x. Points a, b, and c are marked. Let's state the values they represent. Since the scaling function is y equals log x, to find the original value x, we calculate 10 to the power of y. For point A, y is 2, so the value is 10 to the power of 2, which is 1/100th. For point B, y is 0, so the value is 10 to the power of 0, which is 1. For point C, y is 1, so the value is 10 to the power of 1, which is 10. One crucial property of a logarithmic scale is that equal distances on the scale correspond to equal ratios of the original values. Take the distance between points A and C. That's a distance of 1 minus -2, or 3 units. On the original scale, the ratio of values is C over A, which is 10 divided by 1/100th, or 1,000. Notice that this ratio, 1,000, is 10 to the power of 3, the same as the distance on the logarithmic scale. This demonstrates why logarithms are so useful for comparing very different magnitudes. We have now seen how logarithmic scales provide a powerful way to visualize and analyze data that spans many orders of magnitude by transforming large ratios into manageable differences. We will now apply what we've learned to two significant real-world contexts: the Richter scale for earthquakes and the pH scale for acidity. The Richter scale measures the magnitude m of an earthquake, which is related to its intensity I by the formula m equals log of I over I0, where I0 is a reference intensity. Each increase of 1 on the scale means the earthquake is 10 times more intense. A common misconception is that a magnitude 6 earthquake is twice as intense as a magnitude 3 earthquake. This is incorrect. The difference in magnitude is 3 units, which means it is 10 to the power of 3, or 1,000 times more intense. Therefore, a magnitude 6 earthquake is 1,000 times more intense than a magnitude 3 earthquake. This shows how quickly intensity grows on a logarithmic scale. Next, let's explore acidity. The acidity of a solution is measured on the pH scale. The pH is given by the negative logarithm of the hydronium ion concentration, C. This formula is pH equals negative log of C. A lower pH indicates a higher concentration of H3O plus ions, and thus a more acidic solution. A neutral solution has a pH of 7. Let's find the pH of a solution with a hydronium ion concentration, C, of 0.00234 moles per liter. We plug the value of C into the pH formula. Using a calculator, we find that the pH is approximately 3.63. Since this is less than 7, the solution is acidic. Now let's go in the other direction. What is the hydronium ion concentration in a solution with a pH of 7? We set the pH equal to 7 in the formula and solve for C. This gives 7 equals negative log of C, or negative 7 equals log of C. Using the definition of a logarithm, C must be 10 to the power of negative 7. This is the concentration of hydronium ions in pure water, which is a neutral solution. Today, we've covered the definition of logarithms in base 10 and E, learned the three fundamental laws of logarithms, explored logarithmic functions and their graphs as inverses of exponentials, and applied these concepts to logarithmic scales like the Richter and pH scales. If you're seeking to deepen your understanding of these and other topics in the IB, A-Level, or IGCSE curricula, consider contacting DAR tutors for expert tuition. Our team of experienced educators is dedicated to helping you achieve your academic goals. You can find our contact information on our website. Now, let's practice with some IB-style questions. Worked solutions will be provided to help solidify your understanding. Question 1. Without using a calculator, simplify 2 log 5 minus log 40 plus 3. Take a moment to think about how you would approach this problem. Solution. First, we use the power law to move the coefficient 2 into the logarithm, giving us log of 5 squared. Next, we use the fact that log 10 equals 1 to rewrite the constant 3 as 3 times log 10, or log 1000. Now we have an expression with only logarithms. This simplifies to log 25 minus log 40 plus log 1000. We can apply the quotient and product laws to combine these into a single logarithm. The expression becomes log of 25 divided by 40 times 1000. This simplifies to log of 58 times 1000, which is log of 625. So the simplified expression is log 625. Question 2. Suppose log base p of x equals 5. Find an expression for log base p of 1 over the square root of x. Pause the video and give this a try. Solution. We begin by rewriting the expression inside the logarithm as a power of x. The square root of x is x to the power of 1/2, so 1 over the square root of x is x to the power of negative 1/2. Now we can apply the power law to bring the exponent, negative 1/2, out to the front of the logarithm. This gives us negative 1/2 times log base p of x. We are given that log base p of x equals 5. Substituting this into our expression, we get negative 1/2 times 5, which equals negative 2.5. So the value is negative 2.5. We have now worked through 2 examples demonstrating the application of logarithm laws to simplify expressions and solve problems. Let's continue with 3 more IB-style problems. The first 2 questions involve simplifying expressions, and the third deals with solving a logarithmic equation. Question 3. Simplify the expression 2 ln x plus 3 ln y divided by ln of x squared y cubed. Consider which of the logarithm laws will be most useful here. Solution. Let's simplify the numerator first. We use the power law for both terms, giving us ln of x squared plus ln of y cubed. Then we use the product law to combine them into a single logarithm, ln of x squared y cubed. Notice that this is identical to the denominator. Therefore, the entire expression simplifies to 1. Question 4. Without using a calculator, simplify log base 2 of the square root of 32. Solution. The key is to recognize that 32 is a power of 2. 32 is equal to 2 to the power of 5. The square root of 32 is therefore 2 to the power of 5 halves. Now, we apply the power law and bring the exponent to the front, giving us 5 halves times log base 2 of 2. Since log base 2 of 2 is 1, the expression simplifies to 5 halves, or 2.5. Question 5. Solve for x in the equation less e on x plus 3 equals 4. Remember that the natural logarithm is in base e. Solution. To solve for x, we need to isolate the variable. The first step is to remove the natural logarithm using its inverse. We exponentiate both sides with base e. On the left, e to the power of ln e my cos 3 becomes x plus 3. On the right, we have e to the power of 4. Subtracting 3 from both sides gives us our answer in exact form. X equals e to the power of 4 minus 3. In this scene, we successfully solved 3 additional IB-style problems. Question 3 highlighted the power of the logarithm laws. Question 4 required recognizing a number as a power of the logarithm's base, and question 5 demonstrated how to solve a logarithmic equation using the inverse exponential function. Let's work through one final IB-style question that brings together several of the concepts we've discussed. Question 6. The sound intensity level L in decibels is given by the formula L equals 10 log of I over I0, where I is the sound intensity in watts per square meter, and I0 is the reference sound intensity, which is 10 to the power of negative 12 watts per square meter. We have two parts to this question. First, we need to find the intensity of a conversation with a sound level of 60 decibels. Second, we'll compare the intensities of a conversation and a whisper. Part A asks for the intensity I of a conversation that has a sound intensity level of 60 decibels. Solution for Part A. We start with the formula and substitute the known values. L equals 60 and I0 equals 10 to the power of negative 12. First, divide both sides by 10. This gives 6 equals log of I over 10 to the negative 12. To isolate I, we use the inverse of log. We raise 10 to the power of each side. On the left, 10 to the power of 6. On the right, the logarithm cancels out, leaving I over 10 to the negative 12. Multiplying both sides by 10 to the negative 12 gives I equals 10 to the power of 6 times 10 to the power of negative 12. Using the rules of indices, we add the powers. So, I equals 10 to the power of negative 6 watts per square meter. Part B. A whisper has a sound level of 20 decibels. The question asks how many times more intense the conversation at 60 dB is than the whisper. This is a question about ratios. Solution for Part B. We need to find the ratio I conversation over I whisper. Let LC be the conversation level and LW be the whisper level. The difference between the levels, LC minus LO, is 10 log of the ratio of the intensities. Using the quotient law, the expression simplifies to 10 times log of the ratio of the intensities. Plugging in the decibel levels, 60 minus 20 is 40. So 40 equals 10 log of I conversation over I whisper. Dividing by 10, we get 4 equals log of the ratio. Raising 10 to the power of each side, we find that the ratio of the intensities is 10 to the power of 4, or 10,000. So the conversation is 10,000 times more intense than the whisper. This problem perfectly illustrates the power of logarithmic thinking to compare quantities spanning many orders of magnitude. Let's work through one final IB-style question that brings together several of the concepts we've discussed. Question 7. The half-life, h, of a substance that decays by k% per year is given by the formula h equals the natural logarithm of 0.5 divided by the natural logarithm of 1 minus k over 100. Let's find the percentage rate of decay for a substance with a half-life of 30 years. Part A asks us to find the decay rate k for a substance with a half-life of 30 years. Our objective is to isolate k in the formula. Solution for Part A. We start with the formula and substitute h equals 30. We then multiply both sides by the denominator. Now we divide by 30 to isolate the logarithm containing k. Using a calculator, the natural logarithm of 0.5 divided by 30 is approximately negative 0.00231. To remove the logarithm, we exponentiate both sides with base e. This gives us 1 minus k over 100 on the left, and approximately 0.977 on the right. Solving for k, we find that the decay rate is approximately 2.30% per year. Now for Part B, a question about how half-life and decay rate are related. If we have two substances, A and B, that decay at 1.5% and 0.7% per year respectively, which one has the longer half-life? Take a moment to consider why this might be. Solution for Part B. Intuitively, a substance that decays at a slower rate should take longer to decay by half. This means the substance with the smaller decay rate, K, will have the longer half-life. Since substance B decays at 0.7%, which is less than A's 1.5%, substance B will have the longer half-life. This demonstrates an important inverse relationship between decay rate and half-life. Let's summarize what we've covered in our comprehensive exploration of logarithms. We began by defining logarithms in base 10 and natural logarithms in base e, establishing them as the inverse functions of exponential functions. We then saw how the three powerful laws of logarithms allow us to expand and simplify logarithmic expressions. We also demonstrated how to solve logarithmic equations by using the inverse property. We connected the concept of inverse functions to the graphical relationship between logarithmic and exponential curves, which are reflections of each other across the line I equals x. Finally, we explored how logarithmic scales, like the Richter and pH scales, are essential tools for analyzing data that spans a vast range of values. The practice questions we worked through are designed to prepare you for the level of rigor expected in IB examinations. Remember, mastery comes from practice. Continue to review the concepts and work through additional problems. If any of these topics are still unclear, or if you wish to delve deeper into the IB A-Level or IGCSE curricula, please do not hesitate to contact our tutors. Our expert educators are ready to provide the personalized support you need to excel. Thank you for watching.